Hey, are you looking to add image search to your AI applications? If so, you're in the right place. I'm going to walk through an application I've developed which searches a dataset of Indian recipes using a multimodal LLM, text embeddings, and Postgres pgvector. Then you can decide for yourself how easy it would be to add this functionality to your own applications. Before diving into the code, let's first go over the various components making up this application architecture. Much like any other web application, this has a user interface and an API layer. But what makes this application special is that the API layer is able to communicate with two models, namely a multimodal large language model and a text embedding model. Embeddings, which are generated from the embedding model, can then be stored in a Postgres or distributed Postgres database, such as Yugabyte DB, in order to execute similarity searches based on the user input. So let's walk through the flow and see how everything works. So first, before actually running the application itself, the data set that is used and stored in the database needs to be embedded such that similarity search can be executed. So what I've done is I've taken this data set of Indian recipes, over 4,000 of them to be exact, and I've taken the description column of each of these recipes and sent it to the embedding model. So this embedding model will take all 4,200 plus descriptions and creates a 768 dimensional array of floats representing the text in that description column to be stored in our database. So with the database seeded with all of this data, a user can then send text, image, or both if they choose to do so, from the UI to the API layer, which will do some of the same thing. It'll actually create embeddings for what is supplied to it. What makes this interesting is that if an image is sent, there's an additional step. The image is base64 encoded and sent to a multimodal LLM. So most LLMs that we speak of are taking text and providing a prediction of what text will follow it based on the vast amount of data that it was trained on. But new models are now able to take image, speech, and so forth. So this multimodal model can take a base64 representation of an image and generate a description for us of what it's seeing. In this case, what it supposes the dish is, and describing the various ingredients that it thinks are in the dish. So this description text can then be supplied to the embedding model and compared with all of the embeddings that we're storing in the database with pgvector. So that's how this application works. We're heavily relying on pgvector both for storing embeddings and executing cosine similarity search on the records in the database. So now that we have a brief introduction of all of the components and the application architecture, let's dive into the code and see how this works. The full source to this project is available on GitHub and has been linked down in the description of this video. Here you'll find instructions for installing prerequisites to the project, setting up the database, be it a Postgres instance running locally on your machine in Docker, or optionally a Yugabyte DB multi-node cluster also running locally in Docker. However, you can also install these things in the cloud if you would like as well. You'll also find instructions for loading the schema and seeding it with data, starting the front end and back end of the application, and also ways to test the API layer with curl. So now let's hop over to VS Code to look at some of the more interesting facets of the AI application itself. Let's begin by reviewing the database schema for this application. We start by installing the pgvector extension in our database if we've yet to do so. And then we're creating a simple recipes table. This table includes a description column as well as an embeddings column. This embeddings column is what we'll be using to store a vectorized representation of our description, our text embeddings. These embeddings will be 768 dimensional floats, because that's what's returned from the Nomic embed text model, which we can run locally on our machine using Ollama. This tool allows us to run open source models locally on our machine. However, this application also works using OpenAI should you choose to use OpenAI. If you choose to use OpenAI, OpenAI's model returns 1,536 dimensional embeddings, so this number will be needed to be updated accordingly. All of these instructions are available in the project README. With the database schema set, we can now begin generating text embeddings. I've created a simple script for helping us do this. This script reads in the cuisine CSV file and stores it in a pandas data frame. We can then call the generate embedding function, which we'll go over shortly, on all of the descriptions for all of our recipes and storing it in a new column called embeddings. This data frame can then be output as a new CSV file to be imported into our database. Let's review the generate embedding function next. The generate embedding function is actually quite simple. We can see that all it takes is text, and using either the Ollama or OpenAI client library, embeddings are generated. The LLM embedding model environment variable is being passed to each of them. This is defined in the env file. Here we can see the database configuration as well as the LLM configuration that we're using in this project. If you wish to use OpenAI, you can uncomment these variables and make sure to supply an OpenAI API key as well. With our recipes and their respective description embeddings stored in the database, we can now begin to describe how the API layer works. This is a simple Python Flask API layer, which includes a connection to our database. Here you can see this search API endpoint, which takes both files, in this case image files, and text. If both are provided, a description of the image is provided from the multimodal LLM, and these two values are concatenated in order to create an embedding of both. By using both text and image, we're able to create a more comprehensive embedding with better search results. Let's view how this describe image function works. The describe image function simply takes a file path. Base64 encodes this file and sends it to a multimodal LLM to provide a description of what is being seen in this image. This image is sent with a custom prompt telling the LLM to act as an expert in Indian cuisine and telling it to return 2 to 3 sentences describing the food and guessing any ingredients and the name of the dish if it can do so. This function works with both Ollama and OpenAI, with just slight differences in how these client libraries work. After the description of the image is returned, an embedding is generated using the generate embedding function that was used earlier to generate embeddings for each of the descriptions of our recipes to store in the database. This generate embedding function is called by supplying both any query string that was provided by the UI as well as that image description that was returned. This returned embedding can now be used to execute similarity search on our database, ordering by cosine distance using pgvector. Then the results are returned to the UI in addition to the image description for display. Now we only have one thing left to do. Let's check out this application in action. Here I'm supplying the query text chicken and rice and providing an image from my local file system of butter chicken. Now we will search. Here we can see the backend has described the image as being a creamy orange colored curry. That is definitely in line with the image and the text that we've supplied. And chicken tikka masala is a very similar dish to butter chicken. We also have some other dishes in the result set for chicken stew, chickpea tikka masala, etc., all of which are very similar to what we've provided to the multimodal LLM. So that's all you need to do to get started with using a multimodal LLM in your application. Give it a shot and be sure to reach out if you have any questions.